So good evening everyone, bonsoir à tous et à toutes, and welcome to tonight's presentation of a TF Connects titled Supporting Mathematics Learning in the Transitions Years with Laura Ginny Newman. As I said previously, with Easter and Passover over the next 2 weeks, many teachers are clearly on vacation. We have an extremely small group tonight with, I think, mostly experienced participants. Small groups are always an opportunity to foster participation, so we certainly look forward to addressing your questions and comments throughout the session, mostly through the chat box. Je voudrais profiter de l'occasion pour souhaiter également la bienvenue à nos collègues franco-ontariens. Et en fin de présentation, je parlerai également de notre prochaine session en français dans quelques semaines. We are definitely thrilled to have each and every one of you with us tonight, and it's also our absolute pleasure to welcome Laura Ginny Newman. Laura is a member of the Critical Thinking Consortium, also known as TC Square. She's currently working on the development of a number of resources to support the implementation of critical thinking in the teaching and learning of mathematics. Tonight, Laura will attempt to answer a number of key questions that you may have as math teachers, such as what does it mean to think conceptually, and what strategies can we use to teach our students how to think conceptually and become better at problem solving. So at this point, I'll pass the microphone to Laura and let her keep introducing herself and start addressing these key questions. So Laura, please feel free to click on your talk button to turn your microphone on, and then you can start anytime you want. Thanks, Laura.
Thank you, Michelle, and good evening, everyone. Thank you for joining us at, it appears to be a very difficult time, and I think I've heard from so many others that unfortunately it's not just Michelle and I who have caught this flu virus. There's many people who are not feeling well right now, and perhaps it's the product of this crazy weather that we've been experiencing, or just the product of spring. But I'm just going to warn you that I might cough a little bit and might have to resort to sipping a little bit of hot tea and honey, but I think we're good to go, and I'm looking forward to the session with you this evening. I want to introduce myself in the context of myself as an educator in mathematics, and then I'm going to invite all of you to share with me what grade levels you're teaching, and or if you're not teaching, in what capacity are you working as a mathematics educator. But first I'd like to just share a little bit of my background. I spent over 20 years of my career working as an intermediate mathematics teacher, and spending a lot of time in the classrooms working at that, as well as working with grade 11 and 12 students at the secondary level, working at the post-secondary level in mathematics, and over the last 2 years spending a great deal of time working intensely and closely with teachers, teaching young children right from the age of 3 up to their intermediate years. So it's been a really fascinating journey for me, and it has been a lot of learning for me as well. And I look forward to sharing that learning with you this evening, and the important impact that it's had on student learning in the classroom, in the mathematics classroom. So I would like to begin. I'm just trying to see here. There we go. I'd like to begin by setting the context a little bit, and having you consider the context for what we will be talking and thinking about over the next hour and a half. And if, although this session is on the transition years, what I've noticed that is of significant importance in the transition years is teaching students how to think conceptually. Many of you have probably seen a great deal of work in the area of developing conceptual understandings, inviting our students to develop conceptual understandings. Some of you may be familiar with the work of Barry Bennett, who's done a great deal of work in strategies that help develop conceptual understandings, and some of those strategies you'll see introduced in this session. But really the importance here is really about getting our students to become independent conceptual thinkers so that they don't always have to go through formal instruction on how to develop conceptual understandings. They can independently understand the thinking that is necessary for them to approach new problems and be able to read those problems for meaning and understanding through their thinking about the concepts that they see at play in those problems. So very important to support student learning, particularly in these years as the concepts start to become a little bit more complex, and extremely important in laying the foundations for students to be successful as they continue through the years. I want to start by inviting you to look at the following ideas that I have generated as what I would describe conceptual thinking looks and sounds like in your math classroom. And I want you to think about your own experiences, whether you've done work in developing conceptual understandings or deep learning in your math classrooms, or you haven't, based on your intuitive thinking. If you haven't, based on your intuitive thinking, what do you think this idea of conceptual thinking means? What would it look like and sound like in a math classroom? And I want to give you some time to go over these ideas and actually document which of these you think apply when students are engaging in conceptual thinking. And we have to recognize that these are your initial thoughts, and perhaps they might, in a very fluid way, change or alter over the session. We will revisit this at the end of the session to discuss it a little bit further. But I think it's important for us to have an access or starting point as a group so that we have something in common that we can continue to talk about throughout the session. So using either your pen or a symbol, I'm going to invite you and give you a few minutes to read over these ideas and just to mark down which ones you think, as you consider your experience in the work with your students in the classrooms, which ones, oh, first of all, I'm sorry, this is me not being well. I did ask if I could just quickly see what grade level you teach, or if you're not in the classroom currently, in what capacity are you working in math? So if I could take a moment and just have you in the chat box, write down the grade level you teach, or if you're not currently in the classroom, in what capacity are you working as a math educator? That will also help inform the discussions that we have for the sessions today. Okay, thank you very much. It's extremely helpful because it gives me a sense immediately that for the most part, I'm looking at teachers who are working with other teachers to support their learning about math pedagogy. And I think this is an important idea to share with teachers. So I'm interested in hearing a little bit more about your thoughts as well as we go through the session and how you might actually translate this to classroom teachers. And for those of you who are actually in the classroom, really meaningful for us to hear your voice in the session today, because you're the ones that are, as we say, in the trenches with the students and trying to support student learning in mathematics on a day-to-day basis with students. So thank you for sharing that. That's wonderful. I want to return now back to the slide, and I think I was about to give you 2 minutes, if I can recall correctly. I was about to give you 2 minutes to go through the ideas on this list, and just with an icon or a pen, jot down or put an X or a check mark or something to indicate which of the following do you think have a role in having students engage in conceptual thinking in the classroom? What would it look like and sound like based on your experience? Well, thank you very much for sharing. I'm super excited to see all of the marks across this page. Something I have to tell you generally doesn't happen, but I'm excited because I can see that there's a lot of expertise in our session already. So this is wonderful. I'm going to pause there and just ask you to hold on to that thinking for the session and carry these ideas with you throughout the rest of the session as we discuss what it means to think conceptually in the classroom. We're going to look at defining conceptual thinking next, and we're going to do that by considering what that looks like through a few examples as we try to implement and surface and make explicit conceptual thinking for our students so that we can prepare them for success across the transition years. Now again, I want to highlight that you're going to see conceptual strategies at play in the following examples. What's going to be really important is that we deconstruct what we see from the lens of the thinking that's required for the students to engage in conceptual understanding successfully. I want to reiterate that the importance of this and really the difference in the work that I'm currently doing and a lot of the stuff that's already been published is around the idea that developing conceptual understanding is important, it's critical, but even more so important is empowering our students to understand the nature of the thinking that they have to do. So kind of a bit of a metacognition, the thinking that they need to do in order to, when they're exposed to new problems, new math ideas, they understand what they have to do in order to deconstruct and decode those ideas independently on their own. Because if there isn't a more important skill in helping students be able to understand problems when they first see them, to be able to address without stress and anxiety new problems that they haven't faced in mathematics. This is one of the most important forms of thinking that we have to empower them with in order for to enable them to do that type of thing. So I'm going to offer you a place to record your thinking, and basically it's a small mind map. And as we go through the examples, again, I'd like you to focus on thinking about, as a student thinks conceptually, to develop conceptual understanding, what are they doing, what are they thinking, what are they saying? And I want to put this lens into the session right at the get-go because it is important. Inevitably, one of the questions that always comes up is, how do we assess this? And so thinking right from the very beginning as we look at examples, what a conceptual thinker should do, think, or say, and what those look-fors are really important in informing our assessment for, as, and ultimately of learning from our students. So I want to give you a moment just to jot down if you have any thoughts at this time, and hopefully they have been some new thoughts have been generated, or at least they've been framed by the previous activity that you just did. But I'd like to, if you have a piece of paper, you can either do it in a mind map format or just write down words, or as I would say to students, draw pictures, use equations, record your thinking in any way that you would like, but just take a moment to write down your thoughts about what would define a conceptual thinker. What would a conceptual thinker do, think, and say?
Hello, it's Michel here. I just want you to know that if you need to take a break at some point, we can always make a pause for a few minutes. We just tell people we're taking a small pause. You can go, I just want you to know there's no problem with that. Huh? If you need to take a break.
Okay, thank you. I my tea and honey with me, so.
No, exactly. I could hear that you were doing, but I realized that, you're doing a great effort here, so we appreciate it. But if you need to take a break for a few minutes, we understand. No problem at all.
Thank you. So I'm not going to ask you to share this thinking at this moment. I find it's extremely important, both with students in the classroom and with educators as we learn together, that we can have a moment to record some of our initial thinking about our beliefs around certain things. And not necessarily have to share them, but the importance of this is so that later on in the session, I'll return to this slide, and ultimately at the very end, keeping my fingers crossed that we'll have time, I'll ask you then to share, because at that point you'll have had an opportunity to explore this concept of what it means to be a conceptual thinker, and perhaps to either modify, extend, generate new ideas around this concept, and feel really positive about sharing those ideas. This is a strategy that we refer to at the Critical Thinking Consortium as a launch to learning. It's important because this is accessible to all of your learners, and what I always say in mathematics classrooms to students is that you all come in with background knowledge about mathematics that sometimes you don't think is relevant or important. And it's really important for you to take the time to just write it all down so that you have the opportunity to reflect on that and consider what is relevant, what is important as you start working through new mathematics that you're learning. So we're doing a similar type of thing here, but we're doing it around the idea of a conceptual thinker. I'd like to begin with my first example, and this is based on the consideration of proportionality. There are two examples that I'd like us to consider in a very deep way tonight as we look at conceptual thinking. The first one I think is probably the most significant, and for those of you who are aware of all of the ministry resources that are available on proportional reasoning, you can see that there is a consensus, at least in Ontario, that this is an important idea that really creates a continuum throughout the grades that support student learning, particularly in the transition years. What you'll see that I've done here is I've quickly, for our intentions today, summarized the really important ideas around the idea of proportionality and how it plays out across the grades from 7 and 8 to 9 and 10. And it's really important to start here because, as you will see in the activity and the example that I'm going to show you, all of these things play a role in how I've constructed the opportunity for students to conceptually think about proportionality. It also is important in that what it honors is our understanding of where students are at a particular grade and where they will need to move to next as they continue through the grade so that they can successfully transition across the grades. I'll give you a moment just to read through these. You probably have already been reading through them a little bit as I've been talking. And I'm going to ask you to look for these things as I share a conceptual thinking strategy with you on the next few slides. I would also like to just very quickly share with you, and you'll find these resources on the last slide of the presentation slides. Hopefully we will get to them as well this evening. But they're really important ministry resources that are available. So on proportionality and proportional reasoning, the ministry has tips for RM, they have edu-games, they have monographs that they've written on for proportional reasoning. All really important, but I'm highlighting these also as well so that as teachers, it's important that we know what's out there to support the development of tasks and activities in our classroom. And you will see that not only have I pulled together this continuum based on what the ministry has posted, but I've also built the next series of activities and the strategy that you're going to shortly see pulling in some of the examples that the ministry has already created. And I emphasize with teachers how important it is that our job as educators is to do something in our classroom that's new, but really what we should be doing is tweaking and fortifying our existing work. Teachers should not have to start from scratch because that makes it very difficult for them and it's extremely time consuming. Knowing that there are resources out there that you can pull from, and a lot of the really good ones are already on the ministry website, knowing that you can pull from those or pull from other resources that you're using in the classroom that are available to you is really important in developing really effective and powerful conceptual thinking strategies. So the example here is going to focus on conceptual thinking with proportionality. And what I'm going to ask us to do, although you see two sets of visuals, related visuals on the page, we're going to work through each one of these separately. And I'm going to ask you to consider, because we're a small group, this gives us an opportunity to talk through some things this evening, which is kind of nice. I'm going to ask you to consider the true examples, and I want you to notice the way this has been structured. And again, for those of you who are familiar with strategies to help students develop conceptual understanding, this is probably a strategy you've seen before. It comes directly from the work of Barry Bennett and Beyond Monet. It's called Concept Attainment. And as for those of you who know Barry or his work, he's pulled this from great writers who have thought about thinking in the classroom for many, many years. So you'll notice here that I want to have us taking a look at the first set of examples, which is a true example versus a false example. Now, traditionally, you will see concept attainment listing what we call yes examples and no examples. And what I like to do to really honor the discipline of mathematics is really have students understanding that in math we work with true examples, those that have been tested and generalized over time, and false examples, the ones that highlight why the ones that are true are actually mathematically true. So we call these true and false examples. And I start with a very simple example, you'll notice, of two squares. And then a false example of a rectangle and a square. And I invite students to compare and contrast these two sets of examples and ask them, what do you think is true about the true example that makes the false example false? So what is it that holds true in the true example that is going to be consistent, and how does the false example inform the characteristics or the attributes that make the true example true? So I'd like to give you a few moments to take a look at that example, and we can either talk or in the chat box. If you'd like to grab the mic, just put up your hand and we can have you share your thinking with the whole group, or you can write some ideas in the chat box. I'd like you to take a look at those examples, and through the thinking lens, I want you to consider what thinking do the students need to do as they engage in this comparison. And again, we're only looking at the first example. Or sorry, first set of examples. Okay, absolutely, they're comparing side lengths. Tell me a little bit more about that. How would they know to compare side lengths? And again, feel free to grab a mic if it's easier to talk about it. Okay, great, absolutely. the areas are the same, and that's been done very intentionally so that the students have to look at other attributes. So that explains why they would be looking at length and width. And what are some of the things that they might be saying as a result? Oh, sorry, what are some of the things that they might be saying as a result of what they've been paying attention to and thinking about? Did you hear, was that okay? Thank you. Okay, great ideas. Thank you. So what I want to emphasize here is, as students see this first set of examples, recognize that they wouldn't see the second set of examples. They would see these each one at a time. They would not be seeing all of them simultaneously. And the reason why that's important is that cognitively, the demands of looking at all of this, and in fact we'll be looking at other examples as well, is much too high for students to really digest what it is that they need to think about. So we start off with the simplest of examples, and many of you have probably noticed that the two squares, all of these geometric figures have the same area, and students will talk about that. And so they'll say, the true examples have the same areas, but the false examples have the same areas as well. So what does that tell me? This is part of the math talk that needs to take place with the students in the classroom as they share their thinking, first as they do their individual thinking, and then as they share with a shoulder partner, and then as we talk about it as a class. So as a class, they'll be saying, well, you know, yes, the areas are the same for the true examples, but they're also the same for the false examples. So the false example doesn't really inform my thinking. It can't really be about areas. The students will then start talking about, as you already indicated, so what can I deduce from what I know about the areas? And at this particular grade level, I'm hoping that if they've identified area, they're going to say, well, the length and the side impact on the area of these geometric figures. So now I'm focusing on length and width. You'll notice that I've put in here in the boxes of proportional length and width. I would not put that in there for the students, because that's for our intentions, but that's telling the students a little bit too much, and it's telling them too much about what to think about. So what we want them to do is actually experience the thinking. Students would then start talking about the lengths and widths, and inevitably they're going to say they're both squares. Both squares have the same lengths and widths. In the false example, the lengths and widths are different. And it's a very simple conclusion to draw, but a really important mathematical conclusion when they're thinking about proportionality. My intentions in starting off with a simple example, and by the way, I wanted to start off with a true example of congruency, is often in math we tend to differentiate congruency with similarity. And in actual fact, congruency, shapes that are congruent, are still related proportionally one-to-one. And so separating that in the examples for students so that they don't see that a one-to-one relationship is also a proportional relationship is really misguiding and creates misconceptions. So I wanted to start here and begin with two congruent shapes and two shapes that aren't congruent, and what can we infer from that? What conjectures can we draw from that? And the students will talk about those types of things. Now, They might not get into anything more than that, and at this point they will not have a deep understanding of proportionality. But that's why we layer in another set of examples. So as we move into the next set of examples, I'm going to ask the same question. What do you think the students are going to be thinking about? What's the nature of the thinking that they're going to be doing? And what conclusions are they going to draw? And again, I'm going to invite you to share your thinking in the chat box, or if you'd like to talk, please be free to pick up the mic. So let me break down the questions. First of all, what's the nature of the thinking they're going to be doing? Okay, absolutely they're going to be comparing. Because that's what we've asked them to do. We've asked them to compare what's going on in the true examples and then to contrast that with what's going on in the false examples. And I'm glad that you've picked up on the fact that they will probably begin comparing the areas, because what we've done in the previous example is we've highlighted areas. And we always have to remember what we have our students thinking about just before we engage them in new thinking is going to shape their new thinking. So they're immediately going to be looking at areas, although that might not necessarily be exactly what it is that I'm looking for, but it gives them a point of accessibility, and it's going to help them think through the rest of it. Okay, so they're going to start comparing area. They're going to notice that the area in the first two that's being covered in red is the same, and hopefully extend that thinking to equivalent fractions. Absolutely. How about the false example? Why is the false example false? What are we hoping that they'll notice? Do you think they'll notice anything about the false examples? Oh, that each section doesn't, hopefully, we keep our fingers crossed that they'll notice that each section doesn't represent equivalent area, absolutely. And notice how the example nurtures the paying attention of detail for the students. Conceptual thinking can't happen without paying close attention to details. We'll see that the areas across the two figures are not the same, which is should inform their thinking around the equivalency as well. Are there any other thoughts? What do you think they'll recognize if I'm asking them, what do the true, now if I look at the true examples, what do the true examples, what do they have in common? Because they will have, when they looked at the first two sets of shapes, they will have arrived at a conclusion about what they think proportionality is about, or what it is that the true example, the attributes of the true examples are. And in this case, chances are they're going to say same length and size, because that's what they're going to see, right? Okay, so they're going to see same areas shaded. Hopefully they're going to talk about equivalent fractions. And hopefully they'll actually move to taking a look at that and saying, so what are the equivalent fractions? If they're the same area, what are the equivalent fractions that are being represented here? So they might say, looking at the false example, they might show a misconception here. And again, this example has been very intentionally constructed to get them to understand the concept, to see if they understand the concept of fractions, which is, notice in the first example, I'm comparing two fractions and I can say they're equivalent because they're based on the same whole. If the students are looking at the next set of examples, the false examples, the wholes are now different. And hopefully that's something that they're going to pick up on. Oh, absolutely. Fractions are a big problem right across the grades, right up to grade 12 and even post-secondary. The more we can work with students in fractions and seeing that they understand what a fraction is and they understand what a fraction represents, and more important, that they understand fractions are just another way of representing proportionality is really, really, it's significant. Students fear fractions. They might get the easiest question to answer a problem that is actually quite simple in nature, but the second you include fractions, their anxiety levels go up. And that reflects a lack of confidence in our students to deal with fractions, in that they haven't really deeply understood even the concept of fractions. So conceptual thinking with the notion of fractions, even just fractions alone in the earlier grades, which is something I've done quite a bit of work on in the earlier grades with teachers in the classroom, is significantly important. So I'm glad that you're bringing that up. And then reinforcing it, you'll notice, as we move up the grades and making sure that they don't have the same misconceptions that are very dangerous for them to have, again, is built into this kind of strategy. So here you'll notice that our first example, the students will have said a one-to-one relationship. The false example is not a one-to-one relationship. Lengths of sides and widths are the same. It's not here. That's one important example of proportionality. Now we're moving to fractional representations. And the students here actually, if they've developed comfort level with the relationship between fractions, percents, fractions, percents, and decimals, if they've developed a comfort level with those relationships, they will start speaking to, you know, the percentage of the area that's being covered versus the percentage over here, which gets them to more clearly see that these are not accurate representations of fractions that we can compare. And yes, absolutely, them understanding a whole is so important. In the second example, the proportionality here will be represented in the form of equivalency. And so as the students talk and they generate ideas and the teacher annotates whatever ideas the students are sharing, ultimately they'll get to a point where they're going to write this as 3/4 and they're going to write this as 6/8. And they're going to recognize that this is equivalency that's being shared. And that then gives us a starting point around discussing the role of proportionality in fractions. So in equivalency, proportionality is really important. And how do I make those fractions equivalent? We see that the areas that are being covered are exactly the same, but what happens when I actually see the fractions and see that they are representing the same thing? So again, the students might not completely get there, but they're beginning to see that relationship, particularly when I say, so what is it about the first true example that you noticed and the second true example? Is this still a one-to-one relationship? And how is that one-to-one relationship being represented? So it gives them a chance now to extend their thinking and deepen their thinking around proportionality, starting at a place that's very safe for them. Let's take a look at the next set of examples. Now you'll notice the examples are starting to get more complex and are starting to get richer. And this is because we want the students' thinking to be deepened and their understanding to be deepened. So again, what's the nature of the thinking that they're doing as they compare these two examples? And what conclusions might they draw? And that's a great thing if that's what they're doing, if they're asking what's the same and what is different. Absolutely. Because what we're asking them to do is a lot of comparing and contrasting. And that's their initial thinking, for sure. What are the things they're going to notice? Okay, they're going to notice the size, the corresponding sides of the triangles being represented are different. The angles are the same in the first example for sure. They're going to raise the question of whether the angles are the same in the second. And that's something worthy of consideration. They want to be thinking about, but really important if they surface it. They're also going to be noticing that in the first example, the length of the corresponding sides are doubled. In the second example, they're not going to see that happening consistently. Now we're starting to deepen in the understanding of proportionality. And in this case, the focus is on having students consider scale and similarity. So now we're pushing their thinking beyond just congruent shapes and ideas that they should be carrying forward from their early grades to ideas that are going to be really important for them in grade 7 right through grade 10. How about the next set of examples? What's happening there? And hopefully you can see this well enough. Okay, so they're going to talk about how the shapes fit in, but that's similar with both the true and the false. Now notice how the construction of true and false is important. Is what I want you to consider here the fact that all the shapes, there's a smaller shape that fits within a bigger shape. I want to engage them in that really important thinking around comparison and contrasting. These are false examples. They all have smaller shapes within a larger shape. Is that important? They'll realize that it's not because it's in the false example. What else do they need to consider? They're going to notice that, again, corresponding. Now, this is what's really fascinating. Again, notice how the previous example, the thinking they've done in the previous example around scales and similarity is going to shape their thinking around what they do here. And I'm sure that most of you have noticed that what we're looking at here is the concept of dilations. Okay? So what they'll start doing is bringing their thinking, because what they've done all along is they started off with one conjecture, or generally what we talk about as being one hypothesis, but in math we call that conjectures. They start with one conjecture and they start with a one-to-one relationship. They move to a second conjecture and notice that if I look more deeply, that one-to-one relationship is based on a scale, something that leads to the proportionality. How do I get to my equivalent fractions? In this example, in the third example, they're starting to really deepen that idea of proportionality. All of the corresponding lengths of sides have doubled. In the equivalent fractions, and I'm going to have to quickly go back to it because I can't remember. So I've got 3/4 and 6/8. Again, the doubling is happening here. So they're going to keep building on this, and they're going to bring that to their understanding of dilations. So this is where it gets really fascinating because they begin to explore really deeply each one of these. And what happens is that the students start, based on their previous thinking, because they're testing their conjectures from their previous thinking, they want to see if this still works. Is this idea of a multiplicative relationship present in the next set of examples? And what they'll do is they'll start playing with it and they'll start testing it and they'll begin to realize in all the true examples that this is in fact true. Now what's fascinating about this is the students may have not even done a study of dilations yet, but at being introduced to a visual representation of dilations even before they've studied it, through a study of proportionality, when you get to dilations, the kids will be able to do them in a snap because they'll understand what's going on. Because dilations are all about scalar changes, multiplicative changes to the nature of numbers and shapes. Okay, so, and you'll notice in the second example, what they'll say is, well, does that hold true in all of the examples here? And does it not hold true in the examples and the false examples? And they will see that these are, in fact, sets of shapes in the false examples that are not similar. They don't have a multiplicative relationship. Absolutely. In the false examples, you can't scale up or scale down to make it fit perfectly. Any questions at this point? Again, don't be afraid throughout the session to put in your questions as you may have them as we're going through this. Going to look at another example. Very accessible to our students, but now we're moving from something that they're very comfortable with when they're thinking about proportionality, and that is geometric shapes and fractions, and that they've become more comfortable with that. And now I'm looking at sets. And often when I work with teachers throughout the elementary years, I always reinforce the importance of ensuring that your students develop fractional understandings both in terms of geometric shapes and in terms of sets. Because often what happens is kindergarten and grade 1 students will be looking at representations of numbers as sets, and then they seem to drop off and we do a focus on geometric shapes alone until we start getting to this level where they have to be able to do this. Because really what's being represented here is ratios. So it doesn't matter here as the students look at these, what are we hoping they're going to say? What makes the true examples true? And how does the false example inform that conclusion? What are your thoughts? What are they going to say? That the true examples follow a repeating pattern. Absolutely. What's the nature of that's beautiful, because what's the nature of the repeating pattern? They're doubling, it's growing. Beautiful. Absolutely. They're going to see that multiplicative relationship, that the blue happy faces were doubled, the red happy faces were doubled. Does that hold true in the false example? Absolutely not. Now, I'm so glad that you picked up on the growing pattern, and that's exactly what I'm anticipating, hoping the students will do, because now, remember, I'm moving into the next example, which now becomes a little bit more abstract, but same type of ideas. They're looking at numerical growing patterns, and I want them to extend the idea from a concrete example into a more abstract example. What are they going to notice about the tables? This one gets a little bit more challenging. What are some of the things they might say as they think through it? Okay, absolutely, certainly. That's exactly the things they say. Repeating pattern, if I multiply the days by 3 for each of the days, for each of the x values, it's going to give me the same number, so they see that there's that multiplicative. And now notice that what I want them to be picking up at this point, and as they do it, this is where I want to bring the language into the students, as they look at the multiplicative pattern around proportionality. That multiplicative pattern is that it's always, something's always multiplied by the same number, the constant. Okay, absolutely. And the second one, they're going to notice that that doesn't happen. By the way, what's really powerful is when you see the student saying, and I think one of you had made this note, that the days go up by 1 and the dollars go up by 3. Really, really powerful learning for students as they start going into grade 9 and looking at linear relations. In the second one, they'll say, well, the units go up by 2, but the costs don't go up by anything predictable. So I don't see, now notice, the predictability is around the constancy of the multiplicative relationship. An unordered table would be really interesting. I would think that, maybe what we can do is move on to the next slide. I would think that, maybe here, I might want to throw that in as a tester. So let me go back to this, and let's talk a little bit about, at this point, what might the students be saying are the properties of proportionality. I'm going to give you an opportunity if you want to grab your pen or your text box, however you want to communicate it. If you want to generate your thoughts, please feel free to do it. What might the students think the term proportionality means at this point? Everybody's capturing really important ideas, the idea of a multiplicative relationship, the idea of increasing or decreasing by predictable amount, for sure. It allows us to predict. Beautiful. Comparing size and amount to something else, yes, which is connected to the predictability. Hopefully they're going to be saying things like ratios, equivalent fractions, drawing on all the different examples, connecting the concept of proportionality across the curriculum, which is really important. I agree 100%. So here so far we're talking about increasing or decreasing by predictable amounts. What's really important about that multiplicative relationship that they will have noticed by looking at all those different examples We go back to these examples. What are they going to highlight? With the equivalent fractions, I'm multiplying by 2. With similar triangles or scalar diagrams, I'm either multiplying or dividing by 2. With ratios, what am I doing? As I look at the table, so I've got 2's, 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 and actually now by highlighting this, and I haven't shared all of my examples yet, but by highlighting this, I have to be honest with you, I would probably change this visual and make this so that I'm not constantly multiplying by 2, because there is a danger in the students. However, it's not all the case, so it's a 1-to-1 relationship. There's a 1-to-2 relationship, 1-to-2 relationship. Here, there's a wide range of relationships in terms of the proportionality. Here it's going back to a 1-to-2, so I want to be careful that perhaps maybe I would change this a little bit more to make it richer. And here I've gone to a 1-to-3 relationship. So what have you noticed about all the different numbers that the false examples are going to highlight? Because the students do talk about this, and it hasn't been put into our list yet. We've talked about repeating patterns. We're talking about that they're increasing or decreasing. What makes something increase and decrease in a repeating way? Which is always a fabulous question to ask students. Notice that no matter what example I'm using, it's multiplying by 2, multiplying by 3, in this case multiplying by 4, in this case multiplying by 2 on one side and 2 on the other side. This gets involved with radius. This is a much larger multiplicative relationship, but in any case where they're actually looking at the geometric shapes, figures, or numbers, the multiplicative numbers are what? The kids don't use, this is where I want to use some additive vocabulary, but the kids generally say they are the same. And that's what I want to say to them. In mathematics, we call that constancy, or they are constant. They don't change. And that captures this idea of exponential functions are predictable as well, because absolutely they are. We want to get to the testers. They've come up with their ideas. By the way, they might not have completely all arrived at this understanding through their conceptual thinking right away. The testers give you an opportunity to reinforce those ideas and help the students who haven't gotten there yet catch up. Okay, so this is where I might say, I've observed what the students are talking about, what they're doing, I've looked at their understanding, I've considered their conceptual thinking, which we're going to get to in a minute, and I also want to be making that conceptual thinking explicit, but I want to highlight some other examples that really test the drawing of their conclusions. You'll notice here, what I've done is I've brought in data management and probability. Okay, so these two questions will very clearly have them thinking about which of these represents true examples or false examples. Some students might argue that they both represent true examples. It's really interesting to hear the conversation. So when we create our testers really have to have some degree of ambiguity in them so that they're debatable. Okay, so we want to give some debatable examples. Students can argue both ways with one of the examples, or sometimes both of the examples. So, what conceptual thinking did the students do with proportionality? Again, I'm going to invite you to look at the following ideas and ask yourself, did you see these things happening? Did the students do this thinking? And if you saw them, if you just want to check off the boxes, and if you have other ideas, if you want to write them in, that would be fabulous. I'm going to give you some time to think about this. How do the students reason through these examples? Okay, tell me a little bit more about how they're generalizing patterns in the chat box if you can. And absolutely, they're comparing and contrasting. We saw that throughout. Okay, they look for numerical relationships. Tell me a little bit more about how they're seeking patterns. Wow, excellent. They're seeking patterns, and this will be a question that they'll raise. They're going to say, is it additive or multiplicative? And it's really important the students understand that proportionality is based on a multiplicative relationship, not an additive relationship. So they're testing hypotheses. They started off with a congruency example with a one-to-one-to-one relationship. They then built to equivalency of fractions example, which they saw that doesn't necessarily have to be. It looks like a one-to-one relationship, but only because the whole has to stay the same. What makes it different? The fractional representation. What is being represented? So absolutely, each time as they look at another example, they're testing and checking their hypotheses. And what we talk about in mathematics is, I like to use the proper word with students, is I talk about that mathematicians make conjectures. They use whatever information they have, even if it's limited, in order to come up with the best conclusion or decision they possibly can make. Okay? Always discourage guessing at any opportunity you can. Do you see anything else happening? I'm just curious to see if anybody noticed something that I hadn't. I notice input-output relationships absolutely with the graph. So hopefully you can see how all of these are playing an important role. Now I'm going to ask you a tougher question. What is the general nature of the thinking they have to do when they compare and contrast, when they hypothesize and test, when they seek patterns, when they generalize those patterns, if they're going to engage in good thinking and sound mathematical reasoning about proportions? So if you look across all of these things, what's the nature of the thinking they have to do? I'm going to give you a little bit of time to think about this because this is a tough question. Whether I'm comparing or contrasting, making conjectures and testing, seeking patterns, generalizing patterns, what is the nature of my thinking? Well, Sandra, I agree with you 100% that if they're looking at the tables, we're starting to move to a much more abstract level over here. And so they might want to actually draw some visuals or do some visual representations or concrete representations to actually, what I like to talk about is to prove that their thinking is correct. So as students do that, I want them to see that representing in a different way is another way to ensure that your reasoning is sound. Absolutely. I want to go back to my tough question. Okay, they need to use their mathematical skills and understandings from across the strands. Any other thoughts? Oh, okay, flexible thinking, good. What do we mean by that? What does it mean to be a flexible thinker? Absolutely. It's fascinating too when I work with teachers in classrooms and we co-plan and then teach and co-debrief, and it's fascinating to see the response of students, by the way, of all ages. The little ones walk out with their hands on their heads and they say, my head hurts. The older students say, I've never had to think so hard. Which is interesting because that's an opportunity to have them talking about, so what was it that you were doing? What was the nature of your thinking? Wow, excellent. So being a flexible thinker means not being constrained by what you think the teacher is looking for or what someone else in the classroom is telling you to believe. Absolutely. A flexible thinker also is able to take their original thinking and modify it and change it based on their learning. Kathy, thank you for sharing that, because conceptual thinking is so important to students being able to innovate and think creatively in the math classroom. Okay, the research strongly supports that students cannot be innovative or creative in mathematics unless they already possess a solid background, a solid degree of background knowledge and understanding to allow them to extend that understanding. And conceptual thinking is all about extending and deepening that understanding. I always say this is a tough question because generalizing when you've seen one set of examples is sometimes hard. And I want to make an important point that if we want students to be generalizing and seeking patterns, they need to see more than two examples. We know that right from the beginning when we have students in in kindergarten and grade 1, when we have them seeking repeating patterns. I can't know it's repeating. I can't know what the pattern is if I only see two terms. So the importance in being able to seek patterns, and unfortunately we've only looked at one example, we've done it several times, but still holistically we've looked at one example that does all of the following rich things. To generalize it is difficult. So here's what's really important about ensuring our students engage in quality inductive reasoning, because that's what conceptual thinking is. Formally, conceptual thinking is just an example of quality inductive reasoning. And for a student, the criteria, the metacognitive criteria they need to use in order to judge whether they've engaged in quality inductive thinking means that they have to do the following things. Whether you are comparing or contrasting, whether you are seeking patterns, whether you're generalizing those patterns, whether you're testing or hypothesizing, these following general things are happening all the time. So students draw a conclusion or make a generalization that has to be supported and explained by their selection or drawing on relevant evidence. So are they looking at, and this is one of the reasons why we want students paying attention to details. We want them to be paying attention to all the details so that they can decide as they're looking at all the mathematical evidence that's being presented to them, and they consider the background knowledge and understanding, and I put accurate in here because we want our students to be drawing on background knowledge and understanding of mathematical truths. There's a real struggle in mathematics that makes it a challenging subject to teach. The reality is, in mathematics, all mathematics is based on absolute truths ultimately is based on absolute truths and correct answers. That's an undeniable fact. And it's one of the reasons that for years, teachers have held strong to, I want to make sure I'm checking to see that my student actually got the right answer. And it's all about right answers. But it's actually more about that, because what teachers who take on that position don't understand is that it's the journey to seek that mathematical truth that actually allows them to generate and understand those truths and generate correct answers. So there's a bit of a cognitive and pedagogical tension in math that takes place, and we have to recognize that both of these are important and one cannot live without the other. Okay? So students here need to be drawing on, paying attention to all the evidence, and knowing what evidence is relevant by connecting it to what they know and understand to be mathematically true. Notice here, we want them considering a full range of alternatives. When I'm comparing and contrasting, I'm considering alternatives. When I'm hypothesizing and testing, I'm considering more alternatives. When I'm seeking patterns, I need to have a lot of alternatives to allow me to do that. And when I'm generalizing those patterns, I need to have the fullest set of alternatives possible. Okay? So they need to consider a full range of alternatives, and they have to assess that alternative using appropriate metacognitive criteria. I'm going to pause here and see if there are any questions, because I know that these ideas are quite challenging. Okay, I'm going to let it sit with you for a little while, because I'm sure there are questions. And by the way, you have my email address, so if you have questions following the session, please don't hesitate to email me. These criteria for quality inductive reasoning are important, because these are our look-fors when we assess for conceptual thinking in our classrooms. Either when we assess for it or students engage in assessment as learning. This is the reason why sharing this with our students in student-friendly language or grade-appropriate language is really important, because this is how we make the process of inductive thinking, good inductive thinking, explicit to our students. We can do all of this other stuff, all of the conceptual understanding stuff, and students will never ever understand this unless we explicitly draw it out from them. And we make it explicit, we post it in our classrooms, we go back to it all the time, every time we hope our students are engaging in quality inductive reasoning. And that's not only when we have them doing conceptual thinking, although conceptual thinking is probably one of the most powerful forms of being able to draw this out of your students. But this needs to be made explicit to all students. If you think about the top achieving students in your classrooms, they are very intuitively already doing these types of things. If we're asking them to engage in rich problem solving in new contexts. I have to put that in there, because if in my classroom all I'm doing is algorithmic procedural teaching and learning, then this is not going to be that relevant. If I want my students to be able to take their learning and their knowledge and their ability to think mathematically and apply it, it needs to be in the context of a problem in a context that they've never seen before, with a problem they've never seen before, which challenges their thinking. The beauty of conceptual thinking is that when you saw the way that we used concept attainment, at every level, the students were forced to push their comfort level beyond where they were already at. This is why the connection that Kathy Youth made to creative and innovative thinking is so important, because that's what creative thinking in mathematics is moving your understanding beyond the familiar. right? And that's what we always want to do with our students. There's another level, two things that we want to assess our students for. So over here, we talked about assessing alternatives using appropriate metacognitive criteria. Many of you are probably saying, what does that mean? You were just too shy to actually express it, or perhaps you do understand it, and that's fabulous, but I want to make it explicit to everybody. When we get to, with conceptual thinking, when we get to metacognitive thinking processes, we want them to be able to understand the criteria. We want them to use the criteria for understanding a concept in order to assess whether that concept is at play in various word problems. In this case, the criteria for understanding proportionality is a lot of the stuff that you identified. Proportionality is relative, it's not absolute relationships, it's multiplicative, not additive relationships, and it's about comparing so that we can predict. When students engage in this kind of metacognitive criteria that we need them to apply to assess the options, there's two things that they need to do. They have to use their understanding, their properties or attributes of mathematical concepts, and they have to ask themselves, one, is my decision or my conclusion consistent with those properties? Two, is it consistent with all of the evidence that has been presented to me? These are the two metacognitive criteria that as students work through developing their conceptual understanding, this is what they're doing all along. They're saying, here's my understanding of what proportionality means. This is what the evidence is showing. As I look at the true example, does that still hold true? Then they apply those criteria again to say, does it hold true when I look at another case or another example? And they look at those criteria again to see whether it holds true when they look at another case and another example. Mathematical truths are based on the exploration of a wide range of alternatives. The exploration and the assessment of a wide range of alternatives. So I'm going to give you a moment to go back to the thinking that you recorded. Is there anything that you would change or add to what a conceptual thinker would think, do, or say at this point? Or are there any questions that you might have? Absolutely, Sandra, and thank you for sharing that, because that's something that I wondered, and I love the fact that you shared that, because putting that in as a tester is really going to push that thinking and make that very explicit. And I'm not sure, I think by you highlighting that has really forced me to wonder whether I've made that explicit in the example. So I thank you so much for sharing that, absolutely. I will make that modification to my data set for sure. Are there any other thoughts or questions at this point? We have about 10 minutes left. What I want to show you is a second example that's based on linear relations, because the grade 9 and 10 curriculum is very solidly grounded on an understanding of linear relations. And as you look at the curriculum expectation and the continuum of understanding that exists, this is a summary, but there is so much more that is there. So it really, really emphasizes the importance of working on this at a conceptual level and through conceptual thinking with your students. What I've done in this example is given you a very simple example, going through exactly what it was that we went through, but this time kind of playing with the Sesame Street of idea. Some of these things belong with the others. So Sesame Street actually did engage very young children in a lot of really good conceptual thinking. Here the example is the students. Again, notice that the students are given a range of alternatives, cases, examples to consider. This is what's really important. If the alternatives do not exist, students have no reason to arrive at a reasoned conclusion. And so we want them to be making sound mathematical decisions or drawing sound mathematical conclusions based on an assessment of a wide range of alternatives that they need to consider. Now, I wouldn't necessarily consider that these 4 examples are a wide range, but they're a starting point. And I just wanted to share this to you as a minds-on that I've used in the classroom to have students looking about and considering the concept of linear relations. I want to make very explicit for you the thinking that the students need to do. So the students are given a thinking template and they're asked how similar are each of the different sets of these options or alternatives. So again, notice they're comparing and contrasting. They're comparing and contrasting. I also would like you to notice how I framed the question. I framed the question to ask the students, how similar are they, not to simply list the similarities or differences. Because when students list the similarities and differences, they're not getting to the thinking we want them to do. They're able to identify a number of qualities that are the same or perhaps different, but they don't get to the importance of the nature of those qualities. So by framing the question around how similar, how different, and having students think about a matter of degree does 2 important things. One, they immediately start paying closer attention to detail. This is one of the habits of mind that are absolutely essential for the success of our students in mathematics. So as soon as I give them a range to consider, it's not easy for them to come up with an absolute answer without paying really close attention to what's going on. Then they have criteria to consider. How do I make the decision about to what degree these are similar? I don't think just about the number of qualities, but I think about the nature of those qualities. So notice the thinking that's involved. They go through each of these, and as we did before, they engage in, and this week I'm going to leave for you because you'll be able to take a look at these, and I actually have them listed on another slide for you to consider. But notice how, again, what we ask them to do by doing this is we're asking students to systematically compare and contrast, to seek patterns, and generalize patterns. Same methods of mathematical reasoning are coming into play. What do you notice as a similarity and difference between this example and the proportionality example that we looked at earlier today? How similar and different was this example that I briefly shared with you with the proportionality example I shared? What do you think? And again, I'm going to ask you to either put a check mark or an X at very similar, somewhat similar, little, if any, similarity. Okay, tell me a little bit more about why they're somewhat similar. And others, please don't be afraid to put down your thoughts. Do you think they're very similar, somewhat similar? Okay, so I'm seeing very similar. And please don't be shy. Tell me a little bit more about why you're seeing somewhat similar. Go back to the slide, absolutely. So what are your thoughts? Very similar, somewhat similar? Okay, so I'm seeing a few of you saying very similar. One of you said somewhat similar. And by the way, there's not a absolute correct response to this. I think it depends on what it is that you're noticing, and sometimes the differences really surface important ideas. So if the person who said somewhat similar tells me a little bit more about what they noticed, that might be really powerful learning for the whole group. Hopefully what you've noticed is, oh, thank you, Anne, for sharing. Okay, so somewhat similar because in the first example, I've got a lot of, I guess, cross-curricular representations. They're cross-strand, right? I can say that in the first set you saw a lot of cross-strand representations. Here I'm seeing a lot of different ways to represent the same concept. So that makes it slightly different, absolutely. So why is that important? And I want to share that importance here. It's important here because once we start getting into formalizing linear relations, this is an extremely rich concept that requires very close investigation of various ways to have the students look at representing linear relations. So I'm glad that you picked up on that. Thank you very much. The other thing that I would like to add that perhaps you may have noticed or not noticed that in the first example we went through a lot more true and false examples. And in this case, there's just a few. I recognize that this is the minds onto a lesson that then extends to students seeing a much wider reach of alternatives that they need to explore, because they really have to explore a wide range of different linear relations with different slopes and different y-intercepts and all those other things. They need to be able to see that they can be represented a lot of different ways and still possess the same common set of properties, mathematical properties. So for those of you who recognize that, that's an important thing to notice as well. Connecting representations, critical here, and thank you, Anne, because what we want the students, and remember we talked about, some of you talked about fluidity, this is where we get fluidity. We get fluidity and fluid thinking and flexible thinking when we have our students constantly working with all the different ways to represent things. And I'm saying all the different ways because they need to be able to flow from one to the other very naturally and to be able to draw on any one of these particular ways when the context demands it. So really important that we enable them to do that. Again, when we go back to good inductive thinking, whether they're doing this, whether they're doing proportionality, whether they're doing algebraic reasoning, which if we had time we'd explore a little bit more too, the quality of their inductive reasoning is always based on these four following characteristics. And this is what we want to surface in our classrooms so that students can self-monitor their thinking and so that as teachers we can engage in ongoing assessment for learning. Some of you may have already picked up just by looking at those 5 different representations that ultimately, again, the metacognitive thinking that the students are doing, as they're comparing and contrasting, is they're thinking about the properties of linear relationships, and these are very concisely designed. Students will probably express all of these in their own words, and they will probably express them in more than 3 different properties. But these are essentially what we want to get to. And they use these properties along with paying attention to all the evidence and the different representations of a linear relationship in order to be able to detect and understand linear relations. Sorry, Anne, I'm just looking. Interesting to note, figure 1. Let's take a look. Yes, well, this is absolutely, and you did notice that because I want to create some cognitive tension here, and I want students to be thinking about maybe one of them doesn't fit, maybe more of them don't fit, but what really that's drawing them to do is to pay very close attention to all the details and the different representations and to draw on what they already mathematically know and understand to be true, making connections across those representations in order to justify their conclusion. So this is what we mean by good inductive reasoning. Now I want to add that in all of this good inductive reasoning, I apologize for that, ultimately what we want a student to be doing is focusing on the nature of their thinking. Okay? Students, if they know how to see concepts at play in a problem, they are able to solve any problem. And so what I want to do is go back to, just before we close, because I know I think it's 1 minute after 9, but I'm hoping I can keep you just for a few more minutes. I want to go back to the original slide that we saw here, and I want to make a clear connection because all of you very clearly already saw, and I'm hoping that you'll see even more clearly how all of these different mathematical processes come into play when we focus on conceptual thinking. Students are representing in a lot of different ways. They're connecting, their reasoning improving as they test and they conjecture. They're developing a deep understanding of the central mathematical ideas. They're selecting appropriate mathematical strategies, models, and tools, and reflecting on the reasonableness of their thinking. All really important. I want to close the session with a closing quote that really emphasizes my strong belief around conceptual thinking. And I'm going to let you read the quote and end with an offering of any questions that you might have before we close the session. So I want to thank all of you for joining the session. If you have any questions or any thoughts, I'll stay on for a little while and see if there's any ideas that you would like to share. And I can address any other questions that you might have. And again, I thank you for spending an hour and a half of your evening during a very difficult time with us this evening. Thank you very much.
Thank you, Laura. Thank you so much for another great session of an extremely high academic level. Hold on, I'm going to switch off your microphone, Laura, for a second.
Sorry, thank you.
No problem. Thanks. Just for interferences. But we really appreciate that you did it despite your cold, and that's extremely gracious of you, and we really appreciate the effort. We could hear you fighting your cold all along the session with the help of a good cup of tea, and we are certainly extremely grateful that that you did that for us tonight, and we hope that you will feel better soon, obviously. I also want to thank all of you for sharing your ideas and experience all along this session and for taking time away from your well-deserved vacation. Clearly because of Easter and a last unexpected bout of flu, we had a very small group tonight, but we certainly appreciate all of you joining us for this session. I would like to take a few more minutes of your time to let you know about a couple of great sessions coming, offered in the coming days. So tomorrow we have an exciting session on using Minecraft in the math classroom. On April 18, a presentation by Carl Pierce titled The Progression of Division. Carl is one of my favorite facilitators. I've worked with him a few times in the past session, and it's always a lot of fun. Then on April 20, Laura will be back again for the second part of her presentation on critical thinking in the primary classroom, a session that you should not miss if you enjoyed part one a few weeks ago. On April 26th, a presentation by Jennifer Evans and Erin Clisby titled Tripping Over Math in Kindergarten. Jennifer and Erin are new to OTF Connects. It will be their very first session, and I warmly invite you to participate if you can, and I certainly look forward to it myself. And then finally on May 1st, our first French session of the year by Suzanne Forrester and Jen Rochon. We have only a very few sessions in French, so if you know French teachers, please forward them the invitation. We only have 2 or 3 French sessions every season. So I'm going to provide you with the links to our calendar and resource page in case you want to browse that at your own leisure. I also would like to tell you about another opportunity provided by OTF and the Ministry of Education. If you're a qualified teacher and you have completed an additional qualification course in math, technology, or kindergarten, you may be eligible for $450 subsidy, and I'm going to paste the link to that page on our website if you want to apply for that subsidy. We value your feedback and we need your feedback, so when quitting Blackboard you will be presented with the opportunity to give us your feedback on tonight's session. The survey only takes a few minutes, so if you can do it tonight, that would be greatly appreciated. And as a new feature of our webinar, we will also offer you the opportunity to fill up a feedback questionnaire, and also we will offer you a certificate of participation to that session. If you don't have the time to do any of that tonight, don't worry. We will send you tomorrow an email with a link to this recording, as well as all the resource that we are sharing with you tonight. In the meantime, I'm going to quickly paste for you in the chat box the feedback survey as well as the certificate of participation, and I will also provide you with the link to tonight's session. It will be live tomorrow morning, and on that page you will find all the recording and all the information you want. So that's it for today, for tonight. I just would like to invite you to follow OTF on social media as well as on the OTF website. I will now end the recording of this session. Please feel free to remain online if you have other questions. Otherwise, I just want to wish you all a very good evening and hope to see you soon on OTF Connects. Bonne fin de soirée à tous et à toutes, et nous espérons certainement vous revoir très bientôt sur OTF Connects. Merci beaucoup.